Hello everyone and welcome back to my channel. In a previous video, I mentioned the reverse skyhook theorem. Some audience asked if I could provide a real-world vehicle data to demonstrate it. In this video, I will use actual parameters to build a model, establish the kinematic equations, and run a simulation. First is the semi-active suspension model. This is sprung mass M2, and this is the spring stiffness KT, and this is the damping ratio CS. Then we add a variable damping coefficient CSH. The damping force is FC. Then the unsprung mass M1. The tire stiffness is KT. And this is a road. The road disturbance is Z0. And the unsprung mass displacement is Z1. The sprung mass displacement is Z2. This is a semi-active suspension model or a quarter car suspension model. Next, we will build the kinematic equations. For the sprung mass M2 times Z2 times S squared. This is acceleration, and S is Laplace factor, equals Cs, the damping force, times Z1 minus Z2 times S. This is the velocity, and Cs is damping coefficient, so this term is damping force, plus Ks, the spring force, times Z1 minus Z2. This term is spring force, and plus Fc. Fc is our control damping force. Alright, for the unsprung mass, M1 times Z1 times S squared equals Cs times Z2 minus Z1 times S. Note here, the damping force and the spring force are opposite compared to the sprung mass. So the spring force Ks times Z2 minus Z1 plus the tire stiffness Kt times Z0 minus Z1 and minus Fc. Alright, last, Fc, the control law Fc equals minus CSH times Z2 times S and times the most important, the system delay ds, and the ds equals t plus 1 over t plus 1. Alright, this is the kinematic equations. We will going to use Python to calculate the Z2 dot over Z0 Bode plot by Python. And we will use actual parameters. Let's see the code. Alright, this is the traditional Skyhook control logic. These are the system parameters. M2 is sprung mass, M1 is unsprung mass, and Ks, suspension stiffness, Cs is suspension damping, and Kt is tire stiffness. Also, for the control parameters, the Tc is the system delay, and CSH. This is the Skyhook damping coefficient. So based on the kinematic equations, I built this code. Then let's run it. Alright, as you can see, the black line, this is the skyhook control, and the dashed line is no control. In around 1 to 2 Hz here, in 1 to 2 Hz, the skyhook performance excellent, effectively reduce the vertical vibration of the sprung mass. However, from 3 to around 9 Hz, in the middle frequency, the skyhook control. However, in the 3 to 9 Hz, the skyhook actually worsens the vertical vibration of the sprung mass. I explained the principle of this in details in a previous video. The answer is the delay in the control system causes the direction of the control force to be opposite to the direction of the sprung mass motion. The solution to this middle frequency deterioration is let the control force act on the unsprung mass. Let's return to the kinematic motion. The control law. We control the z2 acceleration. Now, we change the control law to Fc equals CSH times Z1 times S times ds. So, let the control force act on the unsprung mass. Regenerating the code. Here, I have added control skyhook and reverse skyhook. Let's see the comparison. Run the code. Alright. The black line is unsprung negative skyhook. What I called is reverse skyhook. And this line is the traditional skyhook. And dashed line is no control. As you can see from the curves, the effect of the reverse skyhook control method in the 3 to 9 Hz middle frequency range is very significant. That concludes today's content. I encourage everyone to combine these two videos to learn about the limitation of the traditional semi-active suspensions and their corresponding solutions. The most important thing is to understand the essence of the problem. Building up on this foundation, there are still many innovation ideas regarding semi-active systems, which I will continue to share with you in the future. See you next time.